You cannot reject. When do you reject the null hypothesis? When p value is less than the significance. That indicates it is too far away from what you want to be. I am repeating myself because I am seeing some blank faces. No other reason. Okay, let's get started with this thing and then we'll take a break at about 10:30. So, we are done with inferential techniques, the concepts of inferential techniques. There are many tests depending on the situation. Which test we use when? Most common ones that we will face ever, or we will see references to them when we do our regressions or other kinds of time series or whatever things that we do, statistical techniques. Things like this pop up in your outputs. So you need to understand what these are. The most common statistics are the Z test, the T test, a chi-square test, and an F test. The Z and the T are related to our sampling distribution of the means. These two are related to sampling distribution, likewise of variances. But all of them are children derived from normal distribution only. In fact, Z is a normal distribution, standard normal distribution. Same Z-score, nothing different. Same Z-score. Okay? So, we have calculated confidence intervals using Z values, etc. quite a bit by now. That is what is the Z test. Okay. When we were using confidence intervals, we used Z scores. Z is equal to x minus mu divided by standard error. So mu was somewhere between x plus minus Z times the standard error. That is what we said was the confidence interval formula. Margin of error. That is the Z test. Nothing more. That is the Z test. So we will look at all of these. In fact, Z we have already seen, so we will look at T starting now. T distribution. All of them have this name. Distribution is part of that thing. This guy, William Gosset, was a statistician in late 1900s, 1800s, early 1900s. And when he got a job with the Guinness Brewery Ireland as a quality control specialist, he was excited about it. So he said he can go to the brewery, he can start drinking beer and say, well, not good, good, whatever. But then those people were smarter. They said, you are a statistician. You only use statistics to say whether the quality is good or not. So this guy got mad. The whole part of the story is made up. So this guy got mad and he said, okay, I will not name this distribution. He would have thought he would make it B distribution, beer distribution. So he said, no, not B. Let me think of it as T. Just T. So it's not beer, it's just T. So T distribution is what he called it. That's all we know. Okay. But him getting a job in Guinness Brewery and all that is fact. What he was doing was, he was using the normal distribution, getting the samples and testing and then making inferences about the overall beer, all the lot that is being manufactured, etc. Take some samples and measure some of the properties of the beer. And he was not getting the right answers. So he felt the normal distribution was not helping him out much. So that's why he made some changes to that. He came up with a new distribution, and that is called a T distribution. T distribution, it's still based on normal distribution. The foundation is normal distribution. T distribution is useful when the sample size is small, less than 30. We said statistically more than 30 is a good sample size. Sample size is small, or when you don't know the population variance. A T distribution is better representative than a Z distribution or a Z distribution. So two conditions. distribution should be used instead of a Z distribution. Let's see what these things are. I'll put a screenshot. Let me do a demo in Wolfram. Okay, so there are a lot of demos here. Wolfram again is a nice site. They don't explain anything, but visually, many of the statistical things we have seen, normal distribution, this, that, everything. So it's a nice one. There is a concept of degrees of freedom. I will talk about that. Have I talked about it yet? No, I have not, because there was no reason to. Okay, now I will talk about it. But you see, this blue guy here is my normal distribution. You can see that. The red fellow is my T distribution. Okay, T distribution. The tails are here, but it's still symmetric. Your skewness will be 0. Kurtosis will be more than the normal distribution. Tails are here. The fourth power deviation from the mean, that will be a larger number. Okay, so this is what it is. But this is dependent on degrees of freedom, a concept called degrees of freedom. So T, the normal distribution, there is only one standard normal distribution. Whatever values you take, there is one Z distribution with a mean of 0 and a variance of 1. T distribution, however, changes as I change my degrees of freedom. So this is one T distribution. Then I increased it. Okay. Now there are 7 degrees of freedom. 7 degrees of freedom. That looks like that. And I keep on going. 22 degrees of freedom. And as statisticians, we end up at 30. 30 degrees of freedom. It's looking exactly like the normal distribution. It overlaps that. Beyond that, whether you use T or Z, irrespective of whatever other conditions, they will give you the same answers. So after all, whatever distribution we do, we have to be interested in the area under the curve. The area under the curve, at this point, whether you use a T or a Z, the answer should be the same. But if I say here, it says 99% of the data plus minus 3 sigma. But in T distribution, that's not true. No? There is still some more data here. The tails are heavier. That won't follow your empirical rule. But once it hits that 30 degrees of freedom, hits 30 or something, it's same. So don't think of these as some strange concepts. It's describing the shape of the data. And if the data looks exactly like some other distribution, it doesn't matter what name you give it. You use the distribution to find area under the curve at some specific value. Any distribution, even the next few distributions will do the same thing. Okay? Formula changes. Who cares about the formula? We do for some part, but that's about it. Okay? So this is my T distribution. Degrees of freedom 1, degrees of freedom 5, and then 30 degrees of freedom, exactly the same. Just like Z-score, what should we have here? A T-score. You already know that. And we still have not learned anything beyond our mean and the variance. Mean and the standard deviation. My confidence intervals or anything, but some number of standard deviations away from the mean. That's it. So same thing. Okay, so T-score. What should be the T-score? Again, what is a Z-score? Z-score, if I have a sample, how many standard errors away is the population mean from this? I want to understand. In the T-score also, I would like to understand the same thing. The shape is different, but I still want to understand the same thing. How many standard errors is my sample mean away from the population mean? It's the same thing. Instead of a Z, I have a T. In a Z, I had sigma, the population standard deviation. T distribution is used when population standard deviation is not known. So what do? I use my sample standard deviation as a representative of the population. We used it back then. In fact, I could use t-distribution there to solve that same problem. So, S divided by square root of n. Sample standard deviation is being used. That's it. But we also saw, so that is the t-score. What was the z-score? X-axis. T-score is also x-axis. But we saw that the t-distribution changes with degrees of freedom. There is something else that determines the t-distribution. What is the degrees of freedom? Degrees of freedom is seen in two different ways in statistics. One with respect to sample size and one with respect to the number of parameters that you are trying to identify. So we will see that in a linear regression, if I have 5 independent variables that I am trying to estimate, then it can be determined based on that also. So we will come to that slowly. At this point, sample size is one of the ways. Let's understand how it is. And so let's say, well, we take this group here. Any group. In the morning when they came, I don't know who came first, but let's say all these 3 chairs were empty. Okay? So Kashyap comes. He says, oh, well, where do I sit? Here. He has a lot of choice, a lot of freedom. So, and he is unable to make decision. Finally, he made a decision, sat here. But he had freedom. Kashyap had freedom here. Then Abhishek comes. Abhishek comes and sits, so 2 chairs empty. Well, he has freedom. He can pick this one or this one. He picks it. So Abhishek sits here. Finally, Venugopal comes. This is the only chair left. Does he have freedom? No. Unless he wants to sit in their laps or something, he has no freedom. He wants to sit in an empty chair. So I have put a constraint. What is the constraint? Number of chairs available is 3 only. With that constraint, when 2 people have picked, the third one doesn't have freedom. The degrees of freedom only 2. N minus 1. Because I have put one constraint that there are only 3 chairs. One constraint, 1 degree of freedom gone. If I put 2 constraints, 2 degrees of freedom gone. Like that. Okay? Any number of constraints I put, that many degrees of freedom are lost. If I calculate the mean of a sample with 5 data points, and then I say this sample mean is an estimate of the population. This is fixed, let's say. Now I take another sample. If I have to come to the same estimate, then I have 5 data points here. I take another 5. 4 data points can be any value, but the 5th data point is constrained by the fact that the mean is fixed. The mean should be the same. Now I can't have it. So if I add the original data, let's say 3 data points, 1, 2 and 3. What is the mean? 2. 2 is the mean. I say this mean is fixed now. This is the estimate. Now I get another sample. The data I get is 4. Free, any value can happen. Second data point I captured, 5. Any value can happen. Third value, if my mean is fixed at 2, can it take any value? No. So 4 plus 5, 9, and the total should be what? 6, no? So minus 3. The third data point has to be minus 3. So that sum is 6 divided by 3, 2. I get again the same average. So because I have put this restriction on the estimate, one estimate I have calculated. So that is what happens. You see the concept of the degrees of freedom? Most of the time, when we use sample size as the measure for the degrees of freedom, it's always n minus 1. Okay, n minus 1. In fact, when we calculate our standard deviation and variance, how do we calculate that for a population? What were we doing? Variance for a population was? X minus mu squared, sum of all those divided by if I do the same thing for a sample, I put n minus 1. I am calculating sample mean and using that to calculate variance. So if I use a sample mean, then what will I do? X minus not the population mean. I use x minus the sample mean, and I am using that as an estimate. So I am losing 1 degree of freedom there. So I divide by n minus 1. So that is the concept. So in that sense, whenever you calculate any averages, you are saying I am dividing by total number of data points, but that is essentially dividing by total number of degrees of freedom. In a population, all the n are free to pick anything. So I am dividing by n degrees of freedom. So it is not the number of data points or something, it's dividing, averages are calculated while dividing by the number of degrees of freedom. I am emphasizing that because that will come in future, future concepts, we will be dividing by various different things, but all of those are just calculating averages. Calculating by dividing by the number of degrees of freedom. N minus 1 is normally the thing. We will see in different situations how to calculate that. But that's one thing. Once I have that, a t distribution, the properties of a t distribution, we saw that visually. The mean is 0. It was just like my normal distribution. The variance is given by nu divided by nu minus 2, where nu is the degrees of freedom. That is changing. The variance was changing. It was, and as degrees of freedom become large, let's say 100 degrees of freedom. 100 degrees of freedom means what is the sample size? 101. Degrees of freedom is sample size minus 1. So if degrees of freedom is 100, sample size is 100 plus 1. So 101. Okay? Just for you to start getting used to the concept of degrees of freedom, nothing else. So if degrees of freedom is 100, what will be the variance? 100 divided by 998. Close enough to 1. If the mean is 0 and the variance is 1, what is that distribution? Standard normal distribution, the z distribution. And that's what we saw. They were overlapping. But at small degrees of freedom, the variance will be different. The tails are heavier. Okay. That's all there is. And once that is there, I use my why am I doing this? Only to do my confidence intervals and hypothesis testing. Inferential statistics. And so, the confidence interval is the same thing. X bar plus minus, instead of z standard errors, it's t standard errors. Rewrite it to t-score formula. T was x minus mu divided by standard error. Understand? You rewrite that. X bar plus minus 3 times this. Mu is going to be within that. Just derive from the same thing. Alpha. Okay, so now the same alpha that we did, significance level is what we need. Because we need to know different, the t-score corresponding to different significance levels. Let's see how we do that. Here is the t-table. Just like a z table, there is a t table. Next we go to chi-square, there is a chi-square table. We go to f table. W, whatever alphabet you pick up, everything will have a corresponding table or a function. So, what was so here I think it is PT and QT, just like P norm, PT, Q norm, QT, we will remember QT. Okay, so remember that. But table, in z-score, what did we have? This was up to the first decimal of the z-score. This was the second decimal of z-score. Here, this is the degrees of freedom. This is the significance level, alpha values. In Z table, this was all the probabilities, area under the curve. Here, these are all t-score. Let me tell you how they are. Visually, they mean the same thing. In the Z table, the first decimal and the second decimal combined. In this thing, what was it giving me? Huh? Z-score. So Z-score, what is the Z-score? It's not the area. Z-score is the x-axis value. In the Z distribution, Z are the x-axis values. Okay, and then all the other values here, they were giving the probability, the area under the curve. In the T distribution, this is all the T-scores. These are all the x-axis values. And these are alpha values, the area under the curve. Okay, so now let's solve a couple of problems and understand what it is. And then that will be discussion and we will take a break. Let's solve one example, then take a break and solve another example, and then we move on to chi-square, I think. So the labeled potency of a tablet is 100 milligrams. We take tablets for various things. And just like the beer quality control for these tablets is being done. And 100 milligrams should be the population mean. I want to understand, based on the sample of 10 tablets, the 95% confidence interval, where will the true mean be? And these are the 10 samples, 10 data points in that one sample. First tablet 98.6 milligrams, 102.1 milligrams, like that. Problem clear? Okay. So mean of these 10, 100 milligrams, standard deviation 2.48, degrees of freedom, 10 points are there, 9 degrees of freedom. 95% significance level, my confidence level, so confidence interval is 95%, so significance level 5%. I want the confidence interval symmetrical part. So 2.5 in both sides. Of these 10 samples.
That time we use
N minus 1 is what we use. Correct. Okay. So now tell me the confidence interval. Not the final number, just tell me the process, the path. So x 101.24 plus minus. I don't know the t. Okay, so t times 2.48 divided by square root of 10. That's it. All I need is my t. The table will give me t. What does the table need for me to give the t? Degrees of freedom and the alpha value. That's the only thing that is available. Nothing else is available in the table. Degrees of freedom, alpha value, and then it gives me the t value. Okay. So degrees of freedom 9. Alpha value, alpha by 2. So we are interested in 1/2 of it, 0.025. 2.262. That's the t value that I have to use. Okay? If it had been a z distribution, what value would I have used? 1.96. For 95% confidence interval, it was 1.96. It is not 1.96, it is 2.26. And if you see, going down the thing, for infinite degrees of freedom, it goes to 1.96. It's the same as the z value. For 120 degrees of freedom, it's not 1.96, it's 1.98. For 60 degrees of freedom, it's exactly 2. For or 30 degrees of freedom, or sample size 30, so 29 degrees of freedom, 2.045, 2.04, 1.96, 2.04, we can as well just round it off to 2, doesn't really matter. You see what's happening here? It's just that at much smaller sample size, there is much heavier tail. So the t value is not 1.96 anymore. Come up with something else. That number is, some adjustment is being made to that z value. Think of it that way. A t value is an adjustment to the z value based on the sample size. More than 30 samples, 30 sample size, it doesn't matter whether you use a t distribution or a z distribution. Answer is the same. Okay? So you see now what's happening, and these are nothing but your, so 1.96 was your z score, so these are all t scores, these are x-axis values, and then that gives the area under the curve. So 2.262 if I use, now this is what I have. So the mean of the entire population for that batch of medicines, that tablets that have been manufactured, will be somewhere between 99.47 and 103.01, or a mean of 101.24 with a margin of error of 1.77 milligrams. That's what we have come up with. Okay? And in R, if we do that, this is the R code, 101.24. We calculated that. 95% confidence interval, 99.47 to 103.01. 99.47 to 103.01. But it also gives a hypothesis testing thing. Okay? The t value for this sample is 1.5824. The z value for this sample, where is the z? This sample, where is it? Likewise, the t value for this sample, qt, will give you that thing. Okay? What is happening? So if the t value is this 2.26 is here, let's say, 1.548 is somewhere here. If the sample t value is here, will you reject the null hypothesis? If it is less than the critical value, if it is here, will you, this is the 2.26 here. The sample is here. Will you reject or accept the null hypothesis? Accept.
Yeah, accept it.
It's not the critical region. No? The critical region, I mean, it's too far away from the normal variation. Normal variation is somewhere closer to the mean. 95% area around the mean. So accept. You accept the null hypothesis. What was the null hypothesis? The null hypothesis here was that the mean of the medicines, mean weight is 100 milligrams. That's what it is showing here. True mean. The alternative hypothesis is true mean is not equal to 100 milligrams. Mean is because it's a two-sided thing. Either much lower or much higher. If the tablet weighs much less or much higher potency, both are dangerous. I want it to be around 100. It cannot be 150. I'll die. It cannot be 50. I'll die. It has to be 100. So that's what it's doing. Even the same thing, p value. I want you to start seeing this thing because from now on this is what we do. The p value is 0.148. Is it less than 0.025 or 0.05? Is it less than or more than? More. If it is more, do you reject or accept? You accept. Reject is it is less than that, even further away. So it is more. You are rejecting the null hypothesis. No, you are not rejecting the null hypothesis here. It is more than 0.05. It is. And when is it more than 0.05? If it is here, the area under the curve will be more than 0.05. You can make the decision multiple ways. In this thing, you have a decision that you can make just by seeing this number if you know the corresponding corresponding critical value, the 2.262. Compare the p value with the critical value. You reject the null hypothesis if it is smaller. P value more than the critical value, you reject. Or see, 100 is part of this range, no? 100 milligrams is part of this range. That means, even though this sample gave me 101.24, it is as good as 100. I cannot reject the null hypothesis that it is 100 because 100 is included. Its possibility is well within that range. Either you make the decision using hypothesis test, confidence interval, you will come to the same thing. I'll repeat this with more examples as we keep on doing this. A lot of emphasis on this today. So let's take a break. Let's get a quick tea. Now that the tea distribution is over, let's get some tea. Come back. The example we just solved, pretty simple again. So here is the data, the 20 data points, 10 data points we had, and t.test. T.test is what gives us the output, where you have provided the data, the mean and the confidence level. That's what is to be given. So confidence level is 95. Just change that to 95. And same. If you don't give anything, it will by default take 95. So if you don't give the confidence level, it will take 95. If you want to change it, you have to specify. So T the statistic. If you want to get the T value for that sample, that gives the statistic will give you that standard deviation and whatever not. T dot parameter. The parameter that T distribution means is the degrees of freedom. So T test dollar parameter will give you the number of degrees of freedom. So that's how easy it is to code in R. Gives everything. And the output was the T test output is right that we saw in the PPT. Okay, so let's continue with another example and then we move on to chi-square. So a researcher wants to examine CD4 counts for HIV positive patients at her clinic. CD4 is a immunoprotein or something that protects immune cells. So they are sitting on top of your the CD4. These are CD4 are the immune cells. They sit on top of the immune cells, provide the immunity, and once they are attacked by the HIV virus and they are unable to handle it anymore, that's when HIV positive situation arises, and eventually with a lot of it, with all your immune cells being killed by the virus, eventually develops into a full-blown AIDS. So she took 25 HIV positive patients at her clinic and she measured the CD4 levels for each of them in milligrams per microliter or cells per microliter. So that's what it is. So now we want to calculate a 95% confidence interval for the entire population, mean of the entire population. What would be the population here? All HIV positive patients. Whatever the sample is, age, gender, everything covered there properly. That's the population. And this is the output. CD4, number of patients, 25. The mean of this sample of 25 HIV patients, the mean CD4 levels, 321.4 cells per microliter. Standard error is given, standard deviation is given, then the 5-point summary. Minimum, maximum, median, Q1 and Q3. All this is given. Now I want to build a 95% confidence interval. By the way, if they gave me standard error also, if they had not given me, can I calculate that? Just from this, standard deviation is given 73.8 divided by square root of the sample size. 73.8 divided by 5 is 14.8. The software output gives everything. Sometimes redundant information that you can actually find from other information. It gives you for convenience. Okay, so once I have this, calculate the interval, 95% confidence interval. How do I do that? Sorry? Me in here, just give me the number. Confidence interval, 95% confidence interval. With this information, I don't have anything else. So, if you ask me for anything else, I don't have it. If there is something not available, just tell me what is not available. We'll get there. But confidence interval. P-score we need to calculate, okay? If I give you the P-score, what else? Everything else is available. What is it? So tell me the confidence interval. 321.4 plus minus T times 14.8 to standard error. That's it. I'm only asking that much. Don't think that my question is something more deeper in that. I don't understand anything more deeper than that. I only look for the T value and the area of the curve. It's UTPT. Nothing else. P1, Q1. And just visualize the bell. That's all. Actually, that's all there is. The confidence interval is in that bell. Hypothesis testing is in that bell. I look for P value. What is that P value corresponding to what? I just look at that. 5 or 7 different things you remember. That's it. 5 or 7 different things you see in that, visually in that bell. You know everything. Frankly, you know everything. Okay? Just focus on understanding those 5 or 7 things. Just focus on that. It's as simple as that. So, you told me x bar plus minus the t times that. T value I have to get. Okay? So, t value, how do I get that? From the table, I can read it off. So, the table is t, what is the degrees of freedom? 24. 25 data size, so 24 degrees of freedom. So 24 degrees of freedom, and I am still looking at 95% confidence interval. Because it's confidence interval, it is 2.5 and 2.5 in both cases. So I have to compare with the alpha value of 2.5, alpha by 2 value. Okay? So 2.5 is this. So 24 and 2.5, 2.064. So 2.064 is what I get. That's it. I have everything done. So 95% confidence interval, or the 5, actually this should be 95% confidence interval, or confidence interval at 5% significance level, is the true population mean of the CD4 cells among the population of HIV positive patients is going to be between 290.85 and 351.95. As a data scientist, that is what we come to a conclusion. But as I keep saying, and from now on I will repeat it more, you have to now put the business in the business context. What does this mean? I have given you the value. For that you have to understand the business a bit more, that domain understanding a little bit. For that, when I researched, I found that the US government classifies AIDS under 3 official categories. This used to be the case, now I think they have removed the second one, they just have 2. But for a problem, 3 different categories. Asymptomatic, that means there are no symptoms of AIDS, which means the number of CD4 cells will be more than 500 cells per microliter of blood. AIDS-related complex, ARC, 200 to 499. Less than 200, very few immune cells are left. This is stage 3 full-blown AIDS. That's what it is. Given that understanding of CD4, what do CD4 numbers mean? Once I have understood that, now my 95% confidence interval entirely within this range. AIDS-related complex. This is where the entire population is sitting there. Not asymptomatic, not full-blown AIDS. They are somewhere there. So that's it. What that means, let the doctors think about it beyond that. After that, we should not now learn all medicine and look at if we go to college now get a medicine degree. That's what we don't need, but we are done with that. Our data science job is done. Okay? So that makes some sense. Good. That's T distribution. Okay? So when are we using a T distribution? Just like the Z distribution, when I am trying to make inferences about a population mean based on a sample mean, that's when I use Z or T. Making inferences about means only. Okay. Whenever I am making inferences about means, I have to think Z or a T. Z when the sample size is more than 30 and or the population variance is known. T when the sample size is less. That's it. Okay? So that's how we decide. We can extend this thing if you want, not making an inference about population mean from sample mean, but to understand that two samples that you have taken are coming from the same population or not, then we get into two sample t-tests. But still the same t-test. You get difference between the two sample means. See if the difference is close to 0, then they are coming from the same population, otherwise not. But it can be extended. The same thing, formula slightly changes with that, but it's the same t-test. The process of t-test remains exactly the same. Okay, so t-test when you are making inferences about the mean. T and Z also. Chi-square, what happens is sometimes, and we will come back to our the casino problem. So, you design your slot machines with a probability distribution. You said only 0.1% of the people should be winning that $100. 99.7% or what was that? 97.7% of the time people should lose everything. That's how, as a statistician and as a programmer, you design the system. How do you know it is working? What if 50% of the people are getting jackpots? You have to, casino will go bankrupt. You have to test that, no? So, the chi-square distribution comes into picture when you are trying to understand if what you have designed is working the way it has been designed or not. The probability distribution you have designed it with something, is the data fitting that probability distribution or not? The observed values, are they different from expected values? But we also know, observed values will never be exactly expected. 97.7% means, out of 1,000 people, 977 people should not win anything. But I will not exactly get 977. There is that variation, expected variation around that thing. How far before I say, well, this is too much of variation? Same hypothesis testing concept is the same. Is that too far? Okay. So now we will do chi-square distribution. That's where chi-square comes into play. So to be able to do this, let's say $2, $25, $50, $75, $100. Winning to negative $2. You put $2, you did not win anything. So your winning is, or your gain is minus $2. Your gain is 98. You won 100, but you only put $2. This is how it was designed. To be able to test whether the slot machines are working correctly, I now collected data from 1,000 people. How many won what? 7 people won $100. 9 people won 75, 9 people 48, 965 people did not win anything. 1000 people I am fixing because I collected data from 1000 people. I want the expected frequency from that 1000 people. 977 should not win anything. 8 people should win $25. 8 people should win $50. 6 people should win $75, and only 1 out of 1000 should be winning the $100. But this is the reality. Are these differences acceptable variation or not is what I have to test. So I have just put that data this way because the total frequency here and here, observed and expected, should be equal. That is one constraint I have taken. That is one constraint. So, and now I want to see with that whether they are significantly different or not. Significantly different is the statistical term. That significant is a very key word there. Are they? They are different, I can see that. Are they significantly different? Significantly different would mean they are more than what is expected. Okay. Otherwise, they are different but not significant. It's acceptable. Not. So this is where chi-square comes into play. Chi-square, so every distribution has a corresponding statistic. The Z distribution has a Z-score. T distribution has a T-score. Chi-square distribution has an X-square statistic. What would this be in a chi-square distribution? We don't know how it looks, but where will that statistic be? The x-axis. The t-score is the x-axis. The z-score is the x-axis. Whatever the statistic I am ever calculating is always the x-axis. And I am corresponding area. Whatever the curve might look like, it might look normal or it might look different here. You will see that. But we are looking at area under the curve corresponding to some number. That number is the x-axis values. And the chi-square statistic or the x-square statistic is given by observed minus expected squared divided by expected. Summation of all that. That is the formula for that. Okay. Just by looking at the formula, tell me your rejection zone. In any of these hypothesis systems, there also has to be a rejection zone corresponding to some cutoff we decide. 5%, 1%, 10%. Any distribution, any hypothesis system or not, whatever that might be, even if we have not heard some of the names, there are many distributions. Even if we don't, we have to identify a significance cutoff and then compare whether it is in the critical zone or not. For that comparison, there is a formula to calculate the statistic and some table or some R code to get the probability. Then we make decisions using the same p-value. So we will do the same thing here. But given this formula, will the rejection zone be, will this be a one-tailed kind of a test or a two-tailed test? Most of the time. Theoretically, it is one thing, but practically, will it be a one-tailed test or a two-tailed test? Two-tailed. Why? Two-tailed means you are saying the rejection zone is in both the tails. Okay? Looking at the formula, when will you reject? Understand where is chi-square being used. Chi-square is being used when observed and expected. I am trying to see if they are similar or not. So I will be rejecting only if observed is much different from expected. I will not reject if observed is similar to expected. That's why null hypothesis now. Observed is the same as expected. So, if observed is close enough to expected, x-square values are small or large? Small. For small values of x-square, I will not be rejecting. Observed is performing as expected. Not a problem. Unless you punch the data and make them exactly equal or close, which people test for. So that's where, in some cases, it becomes too careful. But generally, I am rejecting if observed is far much different from expected, which means x square is a large number. It will always be, and being a square, this is always a positive number. There are no negative numbers here. Z score can be negative. T score can be negative. Here we cannot have any negative. These are all positives. For small positive means observed is similar to expected. Large positive means observed is very different. So my critical region pretty much always will be in the right. Okay. Always the far right. Okay. That's right. So just understand any formula or anything you see, just try to see it with respect to the visual curve, how that looks. So calculating this, observed minus expected squared divided by expected, if I do that, observed 965 minus 977 squared divided by 965 plus 10 minus 8 squared divided by, expected by 8 plus 9 minus 8 squared divided by 8 plus 9 minus 6 squared divided by 6 plus 7 minus 1 squared divided by 1. That gives me 38.272. T statistic gives me some statistic. Z statistic gives me some statistic. I want to see, compared to cutoff, where is this? So, is this too high or not? How do I know? I have to compare it with a critical value. Let me just show this again, in case you are not relating it to the other ones. Let's just go to my OneNote. In so my Z's, when I was using my Z test, what do I do now? Just draw that. Okay. And what was I looking for? I have my critical region, let's say 95% confidence interval or 5% significance. Let's say I have my low battery. Okay, good. So, what happened? Oh man. Okay, yeah, got it. So, this is my critical region. This is my Z distribution. Okay. So, how do I make decisions in hypothesis testing? I check for, is my sample here? If my sample is here, what does this mean? So, this is my Z critical, and this is my Z for the sample. Okay? And my sample is here. The area under the curve is this much. I can now decide if Z sample is greater than or smaller than? Okay. Greater than, let's not go with the mathematical. If this is greater than, so it is farther away, greater than, farther away, compared to the Z critical, then reject. Isn't it? Farther away, it's too far away from normal variation, which means the same thing as the P. So this means the same thing as P of the sample is less than P critical. Isn't it? The area under the curve. The area under the curve. The area under the curve here is smaller than the critical P. Same thing. That's how we were using the Z distribution. So I compare either the actual x-axis values and make the decision or corresponding area under the curve. Those are the only two things I do. X-axis value or area under the curve. Both of them will tell me the same answer. Compared to that, is it farther away? Which gives me the thing. So in T distribution, what was I doing? So same way, T distribution also. T distribution was, let's say, for small degrees of freedom, that was heavier tails. So tails are heavier. So T distribution. Now here also, I have drawn my critical T. So critical, let's say critical T is somewhere here. It could be one-sided, it could be two-sided, doesn't matter. So critical T critical, or this is also T critical. And let's say my sample fell, let's say here, this time. Okay? So this is the T of the sample. Now, T, again, and actually all the softwares give the, this only, in the modulus only. If T, in this case, is less than T critical, what is the decision? Then accept. Yeah, fail to reject. Good point. Who said that? If you don't mind, should I throw? Yes. I'm very bad at this. Let's see. Yeah, good. Not that bad. I was so bad that I was studying in Trichy, first year. Kids, we were sitting in the English classes. Who cares about English? Just having fun, and then everyone's sitting, and then chalk pieces you start hitting people, just having fun. You don't know where it's coming from. I knew my aim was not this good, so I was not trying to hit someone far away. Who knows, it will go hit the teacher or someone. So I aimed close. Close means the person sitting in front of me. Nah, it didn't hit that person. Okay, so I'm that bad. But I think with age things are improving. Dyslexia. I will try to use knife-based theorem that might get tested twice or thrice, and then see what is the probability. That's false positive. That's how statistics is. Okay, then accept. Instead of using the actual t value on the x-axis, if I use my t value, what will be the t value? It doesn't like those. Give me the answer or else I will type here. Typing is difficult. So P, man, it's difficult. Okay. Unless Mandesh comes up to this point, it won't. Either way, whether it's on the left tail or on the right tail, its area under the curve is to the left or to the right is more. So P P of the sample is more than P. Okay, you have to live with this handwriting. Okay, then you are accepting it. So when the P value is more, you are accepting it because it is closer. Likewise, in x square, in chi-square, okay, chi-square also will have some distribution. And it might just go not good. But something like that. Whatever. And we said the critical region is to the right. And this value is all x square values. So I find my sample, where is it? I compare with the critical x square. If it is less, I don't reject. If it is more, I reject. Or the p value corresponding to that. Any hypothesis testing from now on you will do, this is what will happen. If this is the sample, what will you do? Not reject. Because, why? Because observed and expected are not that far. Up to this critical I am accepting. Observed minus expected square. But it is not that far. So it is, I accept that they are behaving as expected. Isn't it? Any hypothesis testing, same concept. So this is my chi squared. Okay, I want right distribution. Oh, no, it is there. I have to sit down also. Can you believe that as a kid I used to get prizes in calligraphy? I really did. What was it? Like Steve Jobs. Oh. Well, there are good things to that answer and bad things also. Okay? A brilliant guy, but no more. So, I love what he has done, the math. Okay. This a chi-square parameter we want is the degrees of freedom. Chi-square also only degrees of freedom, nothing else. But chi-square, the shape, what this calculation that we are doing, this actually works out like this. It is nothing but z square. They are all in the same family. So z square, x minus mu divided by sigma squares is a chi-square distribution. That's what chi-square is. With 1 degree of freedom. If there are more degrees of freedom, that many z squares added together make up a chi-square. If there are 10 degrees of freedom, 10 z squares added together make up your chi-square. Just for you to understand that it's in the same family. Okay? The shapes are going like this. Degree of freedom 1, it is like this. Degrees of freedom 5, it's right skewed, mostly right skewed. And at very high degrees of freedom, maybe 20 or 30 or something, fairly normal, starts looking normal. Okay? But it's more of right skewed. And you also notice that the mean, so this is 10 degrees of freedom, the blue. The mean will be somewhere close to 10 only. 20, the mean is 20, 40, mean is 40. So the mean and variance, okay, so that's how chi-square is represented. Chi-square, nu is the only thing. So the mean of a chi-square distribution is the degrees of freedom. And the variance of the chi-square distribution is 2 times the degrees of freedom. That's the property of chi-square distribution. So as the degrees of freedom increase, the variance increases and the mean shifts to the right. Degrees of freedom. More degrees of freedom, the mean shifts to the right and the variance also increases. And it starts getting normal at starts looking very normal. That's the property of the chi-square distribution. So coming back to our problem. Now, we need degrees of freedom. Just like in t-distribution, we needed degrees of freedom. Here also we need degrees of freedom. How do I calculate? I don't have sample size here. I have 1000 I took, but degrees of freedom, how many decisions I am making, I calculated or I estimated 5 frequencies. Okay? Because this is counted, I have given, this is the data I have. But I had to calculate 5 expected frequencies. But I don't need to calculate all 5. I put one restriction that the total frequency, observed frequency and expected frequency should be equal. So based on my probabilities, if I had calculated 4 of them, 5th one I don't need to calculate. It's fixed. 1000 minus sum of all the others. If I say that the total should be 1000, I give you 4 numbers. You can get me the 5th number. That cannot take any value different. If I took another sample, let's say 9 people got $25, 9 people got $50. Remember the numbers. 3 people got $75 and nobody got the jackpot. How many people didn't? Let's say 2 people got the jackpot because they will get counted. So 2 people get jackpot. How many people did not get anything? Same. I didn't plan that. Okay? So 977. I don't have to use my probabilities. I know it has to be 977. It cannot take any other value. These things took some other values. But that is fixed. It has to be there if the total number of people are 1000. So that's why the degrees of freedom out of these 5 categories or classes that I determined, I have only 4 degrees of freedom. 5 minus 1, 4. Okay. And once I have that, so this we have already discussed that it is always to the right. Once I have that, I have a chi-square table. Now in a chi-square table, exactly like your t-table. The first column is the degrees of freedom. The top row is the alpha value, the significance levels. And all of these are my x-axis. Chi-square, x-square values. Because I need to know the critical value and then the actual value of my sample and compare. So here, let's say the blue line is 10 degrees of freedom. Okay, this blue line. And so 10 degrees of freedom is here. And let's say, I think this is 5% or whatever, wherever I put on the line. Okay, 5%. 5% significance level. Okay? So in this table, this value 18.307 is my x-axis value here. That is the x-square statistic. All these are x-square values here. And this 0.05 is my area under the curve there. That's it. That's all there is. Any distribution you take, I am interested in an x-axis value and I am interested in the area under the curve. Corresponding to point. That's it. Keep it as simple. Just see whatever problem comes up. What am I looking for? One of these 2. What do I need? If the area under the curve is given, I need the x-axis value. If x-axis value is given, I need the area under the curve. Once I have those, I compare with the critical value and see whether it is in the critical region or not. If it is in the critical region, reject null hypothesis. If it is not, accept null hypothesis. Entire thing that we did in last class summarized in this one sentence. Nothing else. There is nothing else. Any distribution, any hypothesis testing, this is what we will do. So, chi-square distribution, we will come back to solving that problem. Chi-square distribution is used for 3 purposes. To test for goodness of fit, to test for independence of 2 variables, and to test if about a population variance. You have sample variance, make an inference about a population variance, not a mean. Mean would mean t-test or a z-test. Variance, I have to make an inference, chi-square. Depending on the purpose, the test changes. The process of the test doesn't change. That test has a corresponding statistic that defines the distribution shape. That's it. That's it. So we will do examples of all three of these and solve these problems. So goodness of fit is what we are currently doing. The slot machines have been designed with a certain probability distribution. I am testing if the data is fitting that distribution or not. Goodness of fit. That's what it is. Okay? So at 5% significance level, I want to test that. If the slot machines have been rigged or not. That's what the goal of the management is now in the casino. Are my slot machines working as designed or not? Or someone has messed up with those, giving out more money and then taking a cut. Okay. We might be better off doing that. We may get more change than what we can get in the ATM right now. Okay. What are the null and the alternate hypothesis here? What's the null hypothesis? If this is the problem I am looking at. Null hypothesis has to be decided based on what am I looking for. I am looking to see if the slot machines have been rigged or not. Not rigged. No, yeah, we are all nice people. Good. Default situation. Unless I prove something fishy is going on, I have to assume everything is running as normal. So, null hypothesis. They are not rigged. The slot machines are behaving as designed. The probability distribution. They are working as per the probability distribution that the statistician has designed it. Okay? Not rigged. So what is the alternate hypothesis? Slot machines have been rigged. They are not following the probability distribution that has been designed. What are the expected frequencies? We have already done that. Expected frequencies, we have already calculated that. Because we knew the probability distribution, we calculated expected frequencies. What are the degrees of freedom? 4. We calculated that also. Chi-square table only needs the degrees of freedom. Significance level I decide. I know the degrees of freedom. I find my critical value. 4 degrees of freedom at 5%, 9.488. So this x square value is 9.488. And then I see what is the x square value for my sample. What was it? Anybody remember? 38 point something. Where is that? If this is 0, 9, 18, 27, somewhere here. My sample is somewhere here. What do? Reject the null hypothesis. What is the null hypothesis? Not rigged. Which means they are rigged. Done. As simple as that. As simple as that. Wow, yeah, thank you. Yeah. Okay, so we have answered all these questions. It's done. Reject the null hypothesis. This is the goodness of fit test. So 3 different applications of chi-square. Goodness of fit is this. We will do another problem. Before that, let's understand. Chi-square works with any probability distribution. Binomial, Poisson, normal. So you have assumed that some data follows binomial distribution. You have collected the data. You want to test if it is fitting that or not. Chi-square test. Do it and then you can determine whether it is fitting a binomial or not. That's one of the ways of testing. We will do it with one of these problems. But before that, all chi-square requires is degrees of freedom. In a binomial, what is the parameter you are supposed to know? N is any number of pairs. The parameter A is the probability of success. If the probability of success is known, degrees of freedom n minus 1 standard. If the probability of success is not known and you have the sample data, and from this data you have to estimate the probability of success also. then you lose another degree of freedom. Just like for calculating the variance in a sample, instead of using the population mean, you are using the estimate of that. You sample itself, you are calculating mean and then using that to calculate variance. You lose a degree of freedom there. Likewise, if you are using the sample data to calculate the probability of success, the population probability of success is not given, then you lose another degree of freedom and -2 becomes a degree of freedom. In Poisson, what are we supposed to know? Lambda. That if you know that, n-1. If you don't know that, and this is exactly the problem we will do. I don't know lambda. I have only the sample data. If I am estimating, I lose another degree of freedom because of that. I am using my sample to restrict something else. Okay, n-2. Normal distribution, I am supposed to know mean and variance. If I know both of them, n-1. If both of them I again have to estimate using my sample data, I lose 2 degrees of freedom there also. I get my x bar and s square as estimates. And I lose 2 more degrees of freedom and -3. If I know one and I don't know the other, I lose 1 degree of freedom. Depending on what I know and what I don't know. So let's do this problem right here. So the medical emergency service, the 108 service, and ambulance receives calls at this rate. The day I have distributed 100, so 750 minutes is what? 12.5 hours. Day. Divided that into 5-minute intervals. 5 minutes, 5 minutes, and I am counting. Poisson distribution is always to do with counts. Okay? I am counting how many intervals, how many calls I received. Frequency of the number of calls per interval. Okay? And I want to know if this data is distributed as a Poisson. Is this data fitting the Poisson distribution at a significance level of 1%? This is the data. 18 of those 150 intervals, I did not receive any call. 5-minute intervals. So first 5 minutes, I started tracking. No call.